you today. Our lecturer today is Professor David Gross. He is a professor at the Kavli Institute for Theoretical Physics, which is in Santa Barbara. It's part of the University of California at Santa Barbara. It's a theoretical physics institute that follows much the same model that we follow here. Maybe I should say we're modeled after them, since they've existed for 37 years, and we've existed for 5 years. They're one of the premier research institutes in physics in the world, and that's largely due to David's leadership as director over a 15-year period. David is one of the leading theoretical physicists in the world. He won a Nobel Prize in 2004 with Frank Wilczek, his student, and David Politzer for discovering something called asymptotic freedom, which plays a central role in what's now called the Standard Model, which explains all of the physics that we deal with and see in the universe. He's also won the Dirac Medal, named after one of the leading theoretical physicists of his day, Dirac. And David is here to talk to us today about my life in physics. Please welcome David Gross.
Thank you, John. So it's always a pleasure to see all these high school students. I wonder, why do you guys sit in the back of the hall? You want to get out quickly? Anyway, title of my lecture today is My Life in... Very good. Let's see. Shall we try again? My life in physics, from quarks to strings. And I thought I would tell you a bit about my journey and in physics over my life. And then hopefully I won't talk that long, although who knows. And we'll have an opportunity for questions and discussion. So I'm often, when I talk to students, young students, I'm often asked, when did you decide to become a physicist? Many of them are faced with as you probably are, with questions about what your future will be and what direction you should take. And I don't think, my answer is not one that's very helpful, because I decided to become a theoretical physicist at the age of 13, which was rather early. And I did so because at that age I started reading, not online because it didn't exist, but in books, about the advances in science in the beginning of the 20th century. These are some of the books I read. At the time, 1, 2, 3, Infinity by Gamow, which is still a classic, wonderful introduction to mathematics and theoretical physics. The Evolution of Physics by Einstein, again, I highly recommend it to you. It's still a fantastically beautiful introduction to physics. The Universe, the Expanding Universe, which was just new at the time, by Sir Arthur Eddington. In any case, it was just reading popular science books. Unfortunately, I didn't have the opportunity to attend lectures like this and see models of scientists, but they were there in these books. And I was enormously excited by these introductions to, at that time, modern science. My hero was this guy, whom I'm sure you all recognize, Albert Einstein. And, you know, reading Einstein was amazing. Einstein, that time appeared to me like a god, and what he had managed to achieve just with his mind. And actually, today, knowing much more about him and his work and his success and his failures, I regard him as a colleague more than a god, but at that time he was a god. And he sort of summarized what attracted me to fundamental physics, to theoretical physics. He said the supreme test of the physicist is to arrive at those universal elementary laws of nature from which the cosmos as a whole can be built up by pure deduction. Now that's a pretty arrogant, strong statement about what the goal of theoretical physics is, but it enormously excited me. I mean, it seemed, I like to do puzzles. I was good at mathematics, and doing mathematical puzzles were fun. But the idea of trying to understand the elementary laws of nature from which the real world, the cosmos, could be built up by pure deduction sounded to me like the ultimate challenge, more interesting than these sort of artificial puzzles I like to solve. Now, if you're really interested in this goal, it's easy. It's all spelt out for you. You study hard in high school, and you study math, you study physics, you go to the university, you study math, you study physics, and after much hard work and study, you are brought to the frontiers of the laws of the elementary laws of nature, and which is what I did. And at that time, the frontiers, most exciting frontier for somebody interested in the elementary laws was elementary particle physics, the discovery and understanding of the constituents of matter. What makes up matter? What is all this stuff made of? And what are the laws that act on these elementary particles, these constituents of matter? Well, I was led to Berkeley, where I entered graduate school in the early 60s, to Berkeley, California, which was, fortunately for me, the center of elementary particle physics at the time. They had the biggest particle accelerator that accelerates protons and smashes them together at that time in the world, called the Bevatron. Bevatron actually stands for Jevitron, or a billion electron volts of energy in the collisions. Today we have the Tevatron, 1,000 times greater energies. But this was, at that time, the center of elementary particle physics, and people on the hills above Berkeley were making discoveries every month, discovering new particles, and trying to understand what goes on inside the nucleus. What is the nature of the nuclear force? So, again, inspired to try to understand the the fundamental laws of nature, this is what attracted me. And I must say, at that time in the history of fundamental physics was exactly somewhat the reverse of the way it is today. Experimenters were discovering new particles, new phenomena every month. There was a new discovery, and theorists were totally impotent. Today, the situation is somewhat reversed. Theorists have been enormously successful in explaining what goes on inside the nucleus, say, and experimenters have been frustrated by not finding too much new in the last few decades. Now, this goal of trying to understand what goes on in the nucleus, or elementary particle physics as an experimental science, began a little over 100 years ago. And it's amazing how much has been accomplished in only 100 years. Rutherford, famously, after he won his Nobel Prize for radioactivity, discovered the nucleus. And how did he do that? He did that by inventing a technique to probe what goes on inside the atom, inside the nucleus of atoms, that we still use today. He invented experimental particle physics. And what he did was to try to understand, say, the structure of atoms, in this case gold atoms, was to bombard a gold foil with alpha particles. Alpha particles were one of his discoveries of particles that were emitted from radioactive nuclei. They emitted these particles with a few MeV of energy, and they came out of a little hole here and hit the gold foil and scattered in different directions. And he used this to probe the structure of the atom itself, which until then, no one knew anything about its structure. It was thought to be a diffuse cloud of positively charged something with electrons, discovered a decade or so before by J.J. Thomson, interspersed in this stuff that no one really knew what it was. And what he discovered, or more precisely, his postdoc and his student, Geiger, the Geiger of the Geiger counter in Marsden. So these guys would sit in a dark room for a few hours until their eyes became very accustomed to the dark. And then, back in this picture here, the alpha particles that were scattered off the atoms of gold would hit a screen which would emit light when a alpha particle hit it, and they could measure how many particles came out at different angles by seeing little flashes of light with their bare eyes. Rather primitive technique, but this way of learning what goes on inside atoms by scattering particles off them was, I regard, as the invention of elementary particle experiments. And what they discovered was particles got deviated a bit, but some particles got deviated a lot. In fact, some of them came right back. And this was very surprising. Rutherford said this was somewhat like throwing a brick at a piece of Kleenex and having it come back in your face. You don't expect that unless within the gold atom there's a very point-like object that contains most of the mass of the atom. And Rutherford, just he's an experimentalist, but good enough theorist to use the laws of electromagnetism to figure out what the structure of the nucleus was. And he discovered that it was so small that he could just say it was smaller than 100,000 times the size of the atom. And that's where or most of the mass of the atom and all of its positive charge was localized. Now, this technique of probing the structure of the atom, discovering the nucleus in this case, by smashing particles together, smashing alpha particles off atoms, is what we use today, the same technique. Feynman once compared it to trying to figure out how a delicate Swiss watch works by doing the following experiment. You take two Swiss watches and you smash them together, and you take a picture of what comes out. And based on this picture and many others, you try to figure out what the watch is made out of, what are the elementary particles, and how the mechanism works. What are the laws that govern the structure of the watch? Now, you might think that's a pretty stupid way of trying to understand how a watch works and what it is made out of. But it's the only way we have to figure out what atoms are, and especially nuclei, which are so small. We have no way of probing their internal structure except by smashing them together and seeing what comes out. When I was a starting graduate student, the pictures looked more like this. This is a picture from a bubble chamber of what comes out of a collision between the nuclei of hydrogen, protons, and some other target. Not sure what it was. The outgoing particles would form.
The collision is at the spiral point.
Sorry?
The collision is at the spiraling point.
The what is at the spiraling point?
What is the actual site of the collision?
I have actually no idea. In fact, this could very well be cosmic rays coming into a bubble chamber. But it could be a collision. It could be somewhere here. I don't know. It just looks nice. But the same idea applies. You try to see wherever the collision is here, what comes out by putting these particles go around in circles or spirals because they're charged and there's a magnetic field which makes them turn in circles if it's strong enough. And at that time, I guess you determine the energy by the momentum of the particles, how fast it goes around. This is the kind of experiments that were being done at Berkeley with bubble chambers. And they were discovering new particles, mostly, whenever they smashed protons together with other nuclei. And the theorists didn't understand anything. In fact, Freeman Dyson famously said, 1960, the correct theory of the nuclear force, will not be found in the next 100 years. Now, Dyson is known for making wrong predictions, but this one was really way off. In fact, we had the correct theory in only 13 years from that. Today, we smash particles together using much bigger accelerators than existed then. This is the largest one. Hadron is the name that refers to particles like the proton, the neutron, and here we have protons and antiprotons going around in a 20-kilometer ring, smashing together at 1,000 times more energy than was the case in that Bevatron at Berkeley. This ring goes from, situated between France and Switzerland. This is the airport in Geneva. And the pictures that come out of those collisions look more like this. This is actually a simulation. No, I think this is a real event at the LHC. You see there are hundreds of particles, and the bending is not as extreme. There are strong magnetic fields, but these particles are going very fast. And these are some measure of the energy contained in these outgoing jets of particles. And my experimental friends have to, on the basis of analyzing, both with hardware and with their own analysis, literally billions, trillions of such collisions to try to figure out what goes on inside the nucleus, inside the proton itself. Now, over the years, experimenters following Rutherford's lead have done this for 100 years and discovered more and more particles. So the first particle was actually discovered before Rutherford by J.J. Thomson. That's the electron. Carrier, negatively charged carrier of electricity. The proton was really discovered later, as I explained, by Rutherford. And it took quite a while until the neutron was discovered, the partner of the proton with almost the same mass but no electrical net charge. And it's protons and neutrons, as you know, that make up the nuclei that we are made out of. Somewhat later, shortly afterwards, an anti-electron was discovered, predicted by theory, by relativistic quantum mechanics. And then another kind of electron-like particle, the muon and its antiparticle. And then after the war, when particle physicists were extremely well funded by the federal government, since they had developed a bomb, and maybe if we give them money to build new accelerators, they can build even better bombs, they started building truly large-scale particle accelerators. And when they started smashing these protons together, they produced lots of new particles that no one had ever seen before. In fact, these particles live only for a very short time, millionths of a second or less. They decay into radiation or these stable particles like the electron and the proton. And around the time I started graduate school, there were tons of particles being discovered. At Berkeley, every month or so, there was a new particle being discovered. It was a very exciting time. All of these hadrons, particles that had this strong nuclear force between them, all similar to the proton and the neutron. So it was a theoretical mess. Nobody understood anything, which was just the thing that was, to me, most exciting. Now, to make a long, long story short, by the end of the 1960s, it seemed to be the case that protons appeared to be made out of hypothetical particles that were introduced to explain the patterns of these hadrons that were being discovered, called quarks. Quarks were rather strange as introduced to explain what these hadrons might be made out of, because nobody had ever observed anything but integer electrical charges. We had the electron, which had a negative charge, and the proton had exactly the same charge except the opposite, positive. And the other particles, all those long list of hadrons and pions and sigmas and lambdas and kaons, they all had, if any charge at all, integer multiples of 1, the electric charge of the electron. But quarks were hypothesized to have fractional charges, and no one had ever seen fractional charges. And in that way, people could explain that, assuming the proton was made out of 2 of these up quarks with charge 2/3 and 1 down quark, just 2 kinds of quark, with charge -1/3, whereas the neutron, instead of having 2 ups and 1 down, had 2 downs and 1 up, adding up to 0, could explain not just the structure, the existence of, say, a proton and a neutron, but of the whole family of strongly interacting particles that had been discovered. Now, actually, it was more complicated because if you tried to imagine how you'd put together those particles consistent with general principles together, you also had to assume that there were 3 kinds of up quarks, and we label them by colors. It's just a way of saying they're 1, 2, 3, or red, white, and blue, or red, blue, and green, whatever. They're just 3 kinds of quarks, all the same. That was necessary to get a consistent picture of how you'd put these quarks together to get these families. But the problem, we call those colors, these labels, but the problem was that nobody had ever seen quarks. You know, we definitely can see an electron. That's how it was discovered. If you take an atom, it's neutral. It has nucleus, positive charged electrons, and a cloud around it with negative charge. It cancels out. But you can ionize an atom. If you hit it, you knock the electrons out, and then you make them go in wires, and you build motors and modern technology. It's all based on those electrons you pull out of the atom, and you get ions and freely moving charges, currents, of charge. So if there are these quarks inside the proton and the neutron, well, smash a proton with something else, hit it with a hammer, and out should come quarks. And people did this experiment, starting with Rutherford and going to these very high energy accelerators. They smashed these particles together, but no one ever produced quarks. You couldn't ionize the proton. You just got, instead of getting quarks, you'd get other combinations of, maybe of quarks, but they would all, there'd be no fractionally charged objects that looked like quarks. Well, this is a bit of bizarre, and it really was the case that nobody believed that quarks actually existed. They were just mnemonics, mathematical ways of describing the pattern of particles that seemed to be there in nature, but they weren't really particles that existed in any sense. You couldn't make them. In my opinion, and certainly for me, the crucial experiment was an experiment that, following Rutherford once again, smashed electrons on protons at the Stanford Linear Accelerator in the late 60s. And these experiments discovered that the proton actually, in a dynamical sense, when you probe it with an electron, you can deduce that it looks like, dynamically, like it's made out of quarks, and those quarks are moving freely within inside the proton. When you look at it for us, make a very short span time scan. This experiment, for me, convinced me that quarks were real, and eventually convinced the Swedes. And these people who carried out this experiment won a Nobel Prize for discovering the quark, if you want. Certainly giving evidence that suggested that quarks were real objects. But one was faced with this problem. How could it be that quarks were freely moving inside the proton as if there were no forces between them, and yet they couldn't get out? You couldn't produce them. And it was really trying to explain that freely moving behavior that led me to the discovery of a particular kind of force in nature that could explain that. And the answer has a lot to do with, actually, where is, I'm missing this line here. Oops. Anyway, I'll skip but it has a lot to do with the properties of the quantum vacuum. Now, most of you probably know what a vacuum is, right? Nothing. You empty a vessel of everything that's in it, and you turn off all the stray fields, and there's nothing there. It's empty. That's what a vacuum is, right? But not in quantum mechanics. In relativistic quantum mechanics, a vacuum is not inert, is not empty. In fact, in quantum mechanics, nothing can truly be inert, at rest, with no action. Even a state where you removed all the particles, all the energy, turned the temperature down to absolute zero, still there is action. And you know that from the Heisenberg uncertainty principle. Heisenberg tells us that in order to say something about the existence of an object or its position, you have to observe it. And in observing it, you disturb it and you cause action, which is why you can't have particles, according to Heisenberg, who are at rest at a given position, because when you observe it, you give them a kick. You're light bounces off and kicks the observed particle, makes it move. We call that zero-point motion. And the vacuum itself is filled with particle and antiparticles appearing, reappearing, and fluctuating quantum fields because of this basic quantum mechanical effect. So this is actually a version of what the vacuum looks like that you might take away with you. If you want to think of the vacuum, this is a pretty accurate representation of the vacuum. If you could look at it at distances of 10 to the minus millionth of a centimeter, the size of a proton. So this is about the size of a proton. And we can't see that directly. Can only infer it. This is the result of this represents the result of calculations in the theory of the nuclear force, and tells you that there are these fields, we call them color fields, chromodynamic fields, that mediate the force between these colored quarks. And those fields are present even in the ground state, in the vacuum, because of quantum mechanics, and they're fluctuating. And this is what it looks like in some representation using the theory, which works. So the theory is a theory of charged objects, quarks. And the charge, there's not just one charge like electricity, there are three charges. Those are the three colors. There's the red charge, the blue charge, and the green charge. And here you see, what happened to mine? You see the anti-quark, anti-red quark, red quark. So just like if you take two electrical charges, they source a field, the electric field, and there are these field lines that convey the force, the electric force that one charge has on the opposite charge, pulls them together. The same would be true, exactly the same force law would be true for quantum chromodynamics as it is for quantum electrodynamics. If that were the case, then you could easily pull quarks apart, just like you pull the electron. You give it a kick, you ionize the atom, you pull the electron out. And if this were the case, which classically it is, if you don't worry about quantum mechanics, for quantum chromodynamics, then you could pull quarks out of atoms and make them go in quark wires and have quark motors and be kind of interesting. But what happens in reality is that because of the properties of this vacuum, which is highly dynamical and full of these fluctuating fields, the flux lines are squeezed. The vacuum, it's not that nature abhors a vacuum. QCD vacuum abhors flux. It tries to squeeze it away. And it squeezes this flux into a flux tube. And then the force law between the quarks becomes very different. In particular, at very short distances, it becomes very weak, which explains why these quarks behave like free particles inside the proton. And yet, when you pull them apart, this is actually a result of, again, a numerical calculation of the force, the flux between quark and anti-quark in QCD is squeezed to a tube. Looks, by the way, like a fat string. And that is, again, a property of this theory, QCD, which explains why you can't pull the quarks apart. So it's the same phenomena that says when the quarks get close together, the force is weak. When they get far apart, the force doesn't fall off, and you can never pull the quarks out of the nucleus. Now, theories are fine, but science is based on experiments. And theorists can come up with theories. They sometimes do. But the true judge of whether a theory is correct is not mathematical proof or an elegant idea, but making predictions and testing them experimentally. And in the case of QCD, it took a long time. It wasn't trivial. So whereas the theory was already complete in 1973, 16 years later, this was the nature of the test of this fundamental property of the decrease in the strength of the force as you go from large distances, you can't pull them out, to short distances. And this is sort of the theoretical predictions, which weren't so precise even then. And these lines here are the experimental measurements. Now you might say, okay, all these points do lie on the theoretical prediction. But so does this. A straight line, nothing changes with distance. The force doesn't get weaker, doesn't get stronger, also fits the data almost as well. This is the result now in 2009, 20 years later. These are the theoretical prediction, which is much better, improved, better calculated. And these are now the experimental points from literally dozens of high precision experiments. And you see that this is not fit by a straight line anymore and is really a precision test of the theory. For me, as a theorist, this is enormously satisfying, but equally, and perhaps even more satisfying, is using a theory which is well tested and agrees with experiment to calculate properties of matter that I never imagined we'd be in a position to calculate. For example, your mass. When you get on the scale in the morning and you measure your weight or your mass, where do you think it comes from? So I'm now going to ask the students, tell me, what is your mass? What is the origin of your mass? Anybody know?
Knowledge.
Sorry?
Eating.
What is the origin of your mass? It's the mass of the protons and neutrons that make up your nuclei, right?
Yes.
You agree? Good. 99.9% of your mass comes from the mass of the protons and neutrons. But what gives rise to the mass of the proton? Here we have the proton. Somebody, I'm sure you guys can speak up more loudly when you want to. So what was it I heard? Can't hear. The mass of the quarks. The proton is made out of 3 quarks. Surely we just add up their masses. Everybody agree? You're all wrong. Quarks are almost massless.
Oh.
They weigh almost nothing. They weigh about as much as the mass of an electron, maybe twice. In fact, if they were massless, according to QCD, your weight would only change by a few percent. You'd lose a few pounds. You are pure energy. So remember Einstein, E equals mc squared, which is another way of saying that the mass of an object at rest is its total energy divided by c squared. So what goes on is the following. We have this proton, which is this volume, in which there are 3 quarks, which can't get out because when they try to get too far away from each other, the force pulls them back. So they've got almost no mass. They're moving around at speed of light, almost, within this region, confined by this strange chromodynamic force. But they have energy because they're moving, right? Kinetic energy. And if you add up all the energy of the moving quarks, almost massless, and the massless carriers of the force, the so-called gluons, all massless, or almost, you get a certain amount of energy, which divided by c squared gives you the mass of the proton. So that's a good way of thinking. When you weigh yourself and you say, oh my God, I've gained a few pounds, think about it, that you're just confined energy, and you've gained some energy. But, so that's a picture of what you're made out of and how your mass comes into being. But more precisely, we have all those particles that were being discovered when I was a graduate student, and not we, my colleagues who do lattice gauge theory, which are stupendously impressive computer calculations using QCD of the masses of all those elementary particles that we observe in nature, we can now calculate from first principles. Well, anyway, so successful theories take a long time to be confirmed, but eventually they might lead to this. So this is, when you get the Nobel Prize, the king gives you a medal, and he gives you a check, and he gives you a beautiful diploma. And this is with a picture by a Swedish artist. And you see here the proton and 3 quarks of different colors being held together. And they also have a poster they send around. And here you see their vision of 3 quarks inside the nucleus trying to get out and being frustrated by the strong force that doesn't diminish. Actually, the Nobel Prize Committee got it wrong. You see, they have pictured these fluxes as going along a triangle like this. This is what it really looks like, again, calculated in the theory. You pull the 3 quarks apart, and instead of getting a triangle like this, you get a triad like this. You see the flux goes. But the idea was right. Now, I wanted to share with you some memories of Stockholm, which I hope some of you might be able to attend someday. This is the banquet, since according to Nobel, physics is number 1, first mentioned. The physicist gets to sit next to the queen and the crown princess at this incredible banquet. And I thought I would share with you a time lapse of the preparation and the eating of this for this unbelievable banquet in the town hall in Sweden, which goes on for about 5 hours, 8 courses, and opera and entertainment in the middle. It's quite amazing. And this should be fun. So 2 minutes of Nobel banquet. So what you're going to see here is, this is the empty town hall early in the morning. And they're going to set up. Most of, like life, most of the action is setting up. They're going to set up the dinner, and then people will come in, and there will be roughly 400 waiters who will serve and disappear. There'll be entertainment happening in between the courses here, and then the whole thing will end, and it's kind of amusing. But anyway, so the great thing about this theory and the rest of our theory of elementary particles is that it works. We have this incredible thing we now call the standard model, should be called the standard theory, which answers this question of what are the elementary constituents of matter so far observed. What are the forces that act on them? The electromagnetic, the weak nuclear force, which I haven't much discussed, and the strong force that I was involved in. And there's this mechanism, the Higgs mechanism that you might have heard about. On July 4th, 2 years ago, was announced that its final piece of the standard model was discovered at CERN. This is an incredible theory. Few parameters, it describes just about everything we've ever measured, and in a reductionist sense, everything we've observed so far. It's a theory, fits on one t-shirt. You know, some people walk around with just Maxwell's equations. Well, this is the Lagrangian. This is the formula from which one can, in principle, calculate all those masses of the hadrons and just about everything we observe. It's unbelievably successful. But physics goes on. Well, let me just say a word about the Higgs discovery, which is the most recent of the triumphs of the standard model. This was discovered at this large LHC, which I described, in detectors that are truly immense. I mean, it's paradoxical that to discover the structure at shorter and shorter distances, we need bigger and bigger instruments. That's because we have to pump enormous amounts of energy to get to be able to see at short distances, and big detectors like this. This is a human. These are enormous toroidal magnets. And this is the kind of thing they were looking for. This was an dissipated signal in billions and billions of collisions, which might be evidence for this Higgs particle, necessary component of our understanding of the weak nuclear force, which decayed to 2 photons. These would be the photons coming out. And if you could look and see whether those photons, such an event would produce photons, and you're looking for a bump, a particle with a definite mass. And you'll see here a historical picture of how the events accumulated. This was the events. You see these black lines with big errors before the machine was turned on. So where did the events come from? Well, there are always cosmic rays coming into the detector from outer space. And so there were a few events. You see like 8. And this is what you expect from the theory being the standard model with no Higgs. Just this backward, smooth blue curve. And I turn it on, the machine starts accumulating events, and you'll see what they look like. Do they agree with this blue line, in which case there's nothing new. And this is what happened. Went very fast. We now have thousands of events. The blue line is a perfectly good fit, except for a little bump here. See? Not very spectacular. Oops. Went too fast. Not very spectacular, but you can quantify the probability that that really is meaningful. And it was strong enough, together with another experiment. There were 2 groups, 2 important channels. This was another thing they were looking for in a different channel. This would be a picture that looks like this. 4 of these particles coming out. Experimentalists can easily identify these as muons. These are heavier electrons. And this would be hypothetical Higgs decaying into 4 muons. There are very few such expected events. So this was what happened. They discovered some of those events, only about 15 here, you see. But the background, the expected background, the blue curve, has nothing in this vicinity. So this was, again, a strong signal at the same point, the same mass. Putting these two together, two experiments, they were confident enough to announce 2 years ago, 2.5 years ago, that the Higgs was discovered. So this bump. And in that case, these fellows, surviving number of the people who had been responsible for this theory, received the Nobel Prize just a year later, 50 years after they had made their theoretical proposal. So the time scale in some of these, for nature to say this theory is correct, sometimes can be enormously long. Well, the problems we are working on today are going beyond the standard model, where we believe there's new physics and answers to some questions that standard model doesn't provide. I'll be talking more about that in my other lecture later today, but you won't be here. Let me just flash some of the questions that we ask today in particle theory, what's called high energy theory, or, and for example, we ask, does space have quantum dimensions? No, I see, I have to go here. Okay, let me. Does space have quantum dimensions? So part of our speculations as to what lies beyond the standard model at even shorter distances is that we might reveal extra dimensions of space, which are truly different in a way. Go. Okay. And reveal a new kind of symmetry of space-time called supersymmetry. Another direction we've been moving in is to imagine theories which are not viewed in a certain way, are not theories of particles, like we've traditionally been trying to explain matter. You know, matter is made out of atoms, and atoms are made out of electrons and nuclei. Nuclei are made out of neutrons and protons. Neutrons and protons are made out of quarks, and so on, except that maybe not. Maybe there are also an important role for extended objects like strings. And that's a big focus of theoretical speculation and research. There are other aspects of space-time we are fascinated by. Are there extra dimensions of the usual type, but curled up, so that at each point in space there's a little, in this case, 6-dimensional world, but all curled up so we can't see it because we don't have powerful enough microscopes. And even more profoundly, we have been questioning what is space-time? I mean, you all take space for granted, but over the centuries we've learned that space is much more interesting than just something that's there and that's where points, particles sit. It's dynamical, it's curved, and it responds to energy. That's the origin of gravity. But we're now wondering what space-time is actually made out of. Maybe it's not so fundamental. Maybe it itself has a deeper origin. I just want to end with a pitch to all of you young potential scientists, perhaps. And so I'm often asked, what's your advice? And by young students, what's your advice? And what is necessary to become a successful scientist? So my answer is not that original, but it's pretty firm. You should promote your own curiosity. Don't suppress it. That's a necessary ingredient for success in any scientific field, I believe. You should also not suppress your passion, your excitement. And you will have to couple that with perseverance and hard work. You should, as I'm sure you've been told, but it's true, follow your heart. If you don't know what you want to do, follow your heart. Find whatever it is you enjoy the most and do that. First of all, you'll be better at what you truly enjoy doing. Besides, it's much more enjoyable. Aim high, be ambitious, and be ready to fail. And if you're doing what you really enjoy doing, then that's what you'll be doing most of the time, and whether you succeed or fail, you'll have fun along the way. So that's it, and I hope we have time for questions and discussion.
We do have a question.
How do you fall between supersymmetry and chaos theory, and what are you hoping to see when they reopen the LHC at a higher energy level?
So the question was exactly sure I understood. It had to do with chaos theory and on the one hand and supersymmetry on the other hand. And what do I expect, what do I hope will be seen at the LHC when they start doing experiments in 6 weeks from now? Well, chaos theory has really nothing to do with supersymmetry or much to do with particle physics, where we are trying to probe the simplest possible systems which are at the heart of matter. Chaos theory is something that applies to large collections or of systems with many degrees of freedom that unless we have infinite control, which of course we never do, at some point we lose our ability to predict their behavior. And that happens in the classical world and quantum world and in real life, which has many, many, many different components, but is not much of an issue in high energy physics and particle physics. Supersymmetry, I mentioned briefly, is a wonderfully beautiful speculation that has now been around in the theoretical physics community for almost 40 years, entrances many of us, explains many, but has potential for explaining many of the mysteries that are present still in our standard theory. And some of us are very disappointed that it hasn't yet been discovered. I hope and suspect, and I'm still optimistic, that it will be the next round of the LHC when it arrives at its design energy and runs for the next few years. Maybe not. That's the great thing about physics and science, is that you never know. You're exploring. And whatever it is, we'll learn what goes on at the range of energies that the LHC will propose. But I still have a whole bunch of bets that I will be forced to pay off if they don't discover it, and I still am optimistic that they will. Somebody is, no.
What sparked your initial interest so that, at such a young age, at 13, you realized you wanted to?
Well, I told you what sparked it. Reading books, these books really set me off by Gamow and Einstein and so on. I didn't have, at that time there was no internet. Everything is there on the internet. So I had didn't have much to go on, but it was enough.
have any particular interest in science? Do they encourage you much?
Not particularly, no. They were not scientists. I mean, they encouraged me. They weren't, yeah, but not. It really came from just, if you haven't read some of those books, by the way, I strongly recommend them. And there are many others. Yes.
What's the closest you ever came to quitting physics?
To what?
To quitting physics.
That's an interesting question. Why do you ask that question? No, but I was very lucky. As I said, sorry, I never came close. Why quit physics? It's the best life possible. We can, but life of being a researcher in science, I mean, is just unimaginably wonderful. You get paid by society to do what you really love doing. You get to go around the world and meet people in all cultures and countries and who are doing the same kind of stuff and are passionate about it. You immediately have a relationship as close as you would with anyone living close by. You can not just enjoy making discoveries, which sometimes happens, sometimes you're lucky, but you can follow and enjoy almost as well the discoveries that other people make. You're continually learning new things. You get a chance to teach, which is a lot of fun as well, and to interact with a whole range of people from students to your contemporary colleagues. It's a wonderful life. I wouldn't give it up for anything. Yes?
How do you feel about dark matter, and do you think that we would be able to find it eventually, or it's just far?
Well, it's there, for sure, it seems. There's incontrovertible evidence. So, dark matter is not a subject of speculation, like supersymmetry say. You can observe it. Now, it's been observed around stars and galaxies and clusters of galaxies by astrophysicists. And they've deduced by the motion of other objects that there is matter there that you can't see, and matter that bends light. And so you can see it by its lensing characteristic and map out its structure. So we observationally, indirectly, we don't see the light because dark matter is dark. That's why it's called dark. It doesn't emit light, but it bends light and it attracts gravitationally other matter. So we know it's there. And there are a lot of speculations and theories, models as to what it might be. And there are experiments in space, on the Earth, and at the LHC to observe and detect collisions of dark matter with ordinary matter and to make it in the laboratory, because any kind of matter can be made with energy, m equals E over c squared. So if you have enough energy like at the LHC, you have a very good chance, it hasn't happened yet, but it could happen next month, that they will make finally dark matter. I think that's the one place, because it's definitely there and observed, it's an experimental observational fact, that we have a very good chance of seeing it, detecting it underground, or making it in the laboratory in the next 10 years. I'd be willing to take a whole series of bets on that. You're a high school student. Right?
You explained all this energy, and you've explained there's all this energy in the vacuum. There's all this energy in every proton. Where does all this energy come from?
Someplace it's conserved. So if you were to, well, you see, it's a little difficult since you can't take a proton at ordinary temperatures, like in this room, you can't take a proton apart. So you can't disassemble a proton because the nature of the strong force pulls the quarks together. So if they're infinitely far apart, that would be require an infinite amount of energy. But actually, so
Vacuum?
the vacuum is a vacuum, and by definition, if we ignore gravity, it has no energy. So that picture I showed you was a picture of the lowest energy state of the world. Your picture, the classical picture of the lowest energy state, which we can conveniently call zero energy, and unless we turn on gravity, we're allowed to do that, is of nothing. That's a wrong picture of the lowest energy state. I showed you a much better, correct picture of the lowest energy state, which, ignoring the issues of gravity, we can call zero. Ignoring gravity, again, there's no meaning to where we set it's the lowest energy state. You can't lower it. But in terms of what is there that we would observe if we do an experiment a la Heisenberg, it has these fluctuating fields in it. Yes?
The nature of particles that naturally move faster than the speed of light is...
What is the nature of particles that naturally move at the speed of light?
Well, there's theories about particles that move faster than the speed of light.
There are crazy wrong theories about particles that move faster than the speed of light. That's correct. They're called tachyons. And you can hypothetically imagine, let's imagine a particle that moves faster than the speed of light. You run into all sorts of problems. You can easily, or you might, run into the issue of being able with those particles to travel back in time and kill your grandmother. In which case, you wouldn't be here. In which case, you wouldn't have traveled back in time, killed your grandmother. And so you can run into logical inconsistencies or conflicts with what we call causality, if you admit tachyons. From which you can conclude either we're thinking about it the wrong way, or they can't exist. Nature so far tells us they don't exist, which is pretty good answers. So, yawning or, sorry. No.
What's your opinion on string theories?
Well, you didn't get that from my talk? I think string theory is a very old subject in physics. It is almost 50 years old. And it's really not a theory in the same sense that I was describing quantum chromodynamics. That's a theory. We can make predictions and test it. String theory is more of a direction of current research. As I said, it really seemed to be, when it began, very revolutionary in a sense that the basic objects in nature would not be point-like, but string-like. That's a big change with the past, with the atomic tradition. Today, in my opinion, it's less clear what string theory is and that it's really that different. But it certainly is an enlargement of our understanding of relativistic quantum mechanics, of gravity, and we're in the middle of trying to understand what it is and to turn it from a framework that is much more powerful than we had before to answer some of these wonderful questions and to make a true theory out of it. But it's clearly in the right direction, for sure. But there's a lot to be done. And so, those of you who are as entranced by fundamental physics as I was, the most interesting questions, some of which I've referred to, remain to be solved and will be open for quite a while. So there's plenty of time for you guys to get in and have fun. Yes?
Do you think of gravity as a particle or some kind of force? Or do you think of it as a force
Well, you know, in the way we think about quantum field theory in modern relative, you know, particles and forces are interchangeable. So you can say that the force between two charges, the electric force, is due to the exchange of a quanta of the electromagnetic field, a particle, the photon, the quanta of light. That's one way of describing that force or interaction between charged particles. Or you can say that it's due to the electromagnetic field. So quantum fields, or fields in general, like the electromagnetic field, have waves. Light is a wave of the electricity and magnetism, but waves also have a particle aspect. And in certain cases, the field wave description is better suited and gives a more accurate and easy picture. In some cases, you need the particle description. That's is called a dual nature of particles and waves. It's one of the lessons we learned from quantum mechanics, and seems to occur over and over in physics, that you can think of the same phenomena in different dual incompatible ways. They're just different ways of looking at the same physics. Yes?
Institution today that's comparable to what Berkeley was to particle physics?
Well, you know, Berkeley at the time, I was very lucky, because Berkeley at the time was not just for a short time the center of experimental particle physics. It soon became, you know, what became better than it? Right next door, Brookhaven. Brookhaven had a bigger machine, I don't know, it was maybe 3 times as big a few years later. But Berkeley at the time was also this, you know, a great center of theoretical physics. So which it also wasn't some years later. So these things change a lot. Clearly, the experimental center of particle physics today is CERN in Geneva. The United States, unfortunately, which invented in many ways modern particle physics and led the world in this activity, has, like in many other aspects of science, technology, and everything else, given up, unfortunately.
Why do you think that is?
Well, look at Congress. Look at anything. Why do you think it is? You know, we built the biggest, highest energy machine by far, way ahead of CERN in Texas. It was called the Superconducting Collider. And then Newt Gingrich and his friends came into power and canceled it after spending $2 billion. Yes?
So I was reading somewhere about quantum entanglement and a communication that would be theoretically possible if you could change the spin of the electron and you change the spin of some electron somewhere else. But I also read that it wouldn't be possible. But I want to know why such a...
Well, I think you should, I mean, there is, entanglement is a fundamental feature of quantum mechanics. You can have states, quantum systems, which are correlated, entangled over large distances. You can't do the experiment the way you described it exactly. The description is that if you carry out a measurement here, then somewhere far away, you sort of know what the result of a measurement far away would be. Not that that's a way of communicating or affecting that. It's just a consequence of the coherence of that quantum system. Some people find that strange. Some people find many aspects of quantum mechanics strange. I'm not one of them. I love quantum mechanics. It works beautifully. I don't find it, I mean, it's different than classical way of thinking, but it's the way the world works. And some people make a lot of hype out of testing quantum mechanics over and over again and discovering, my God, it works. So this kind of correlation over large distances, which cannot be causally connected, has been tested over and over again. And surprise of surprises, it works. But there's nothing really paradoxical about it or strange about it. It's just the nature of reality and quantum mechanics. Now, the nature of reality is quantum mechanical. And we have this tradition in physics of teaching you guys first classical mechanics. And then sometimes around now, in your science education or at the university, we'll teach you that quantum mechanics is actually the way things work, and all that classical education is wrong. So some people never get over that, but you should.
Less than